was the little circle. Yeah, I was struggling to get that.
They do the
Oh yeah, so I didn't do it. So, oh, okay. I was like doing them wrong, but then I was like, I did that.
I see the yeah, very quite easy. I see the just jump to the first one and send it to the software versions. And over try it does have
Okay, so a couple of quick announcements. Homework 2 is due next Friday. Okay, so that's the 28th, I think. 27th or 28th, just check, but next Friday. And yeah, I also slightly changed the way to contact TA, so this I think is a little easier than what was there before. So both of them will probably work, but this is just easy. And yes, one thing I wanted to point out is that for shortest paths, a good source for lecture notes is these lecture notes by Jeff Erickson. Okay, so he's not, but he writes very nice notes. All right, so that is a quick announcement for today. And so the last class we looked at local search, and we showed that for this matching problem you get a two approximation. For matching. maybe perhaps we didn't call it this, but yeah, we showed that whatever the solution you get is at least half the optimum. Okay, so those kind of things are called two approximations. Okay, so that's what we showed, and we also spoke a little bit about gradient descent and why it converges, and this was just a very high level introduction to gradient descent. Okay, and then we started talking about the shortest path problem, where it's a graph problem. You have a directed graph with edge lengths, and you're given some u and v, and your goal is to find the shortest length path from u to v. Okay, so you're not interested in the number of hops, you are interested in the total length. So that's the shortest path problem. Okay, and of course we said that if the graph is not weighted, you just use breadth first search, which means all lengths are 1. Okay, and this is time of n plus n. Okay, so breadth first search is linear inside the graph. And yeah, one thing maybe I didn't mention is what happens if you have negative weight edges. Okay, so firstly, is the problem well defined always? Okay, remember the problem is just find the shortest length path, right? And if some of these lengths were negative, then what could happen?
You can go in a loop that has net negative costs, and then you go into loop forever.
Right, so if you had a graph like this, where you had 1, 2, and minus 4, this is the source u, then to get to some vertex v, it's probably better if you just take this loop as many times as you can and then go there. Right? So the problem is not well defined if you have negative cycles. Okay, so this is one thing to just know. Okay, the problem is not well defined. Graph has cycles. Graph has negative weight cycles. Okay. So mostly we will assume that all the edge weights are non-negative. Okay, all the edge lengths are non-negative. Weights and lengths are usually changes. Okay, so we'll mostly assume that they are non-negative. But yeah, so you can still ask the question if there's no negative weight cycles, but there's still some negative weight edges. Okay, so that is still fine. Alright, so that's the definition of problem. And one argument that I was suggesting last time is, okay, we know that breadth first search doesn't work. Okay, because the number of hops doesn't necessarily give you the shortest length of the path. But we said that, okay, start with a solution that you get by breadth first search, and you just do some kind of distance updates. Okay, so you start with some solution. Okay, and we said that for every w, so you have the source u. So remember, we are interested in the path, the shortest length path from u to v. Right? So u we call the source, and v is usually called the same. Okay, so u is the source, and for every w, we try to maintain this this quantity that we call dist of w. Okay. So this is not quite the shortest length path, but think of it as the candidate for the shortest length path. Okay. So this is our current candidate. For length of shortest path from u to w. And just for convenience, I will instead of always saying length of shortest path from u to w, let's just write it as d of u comma w. So this is not this is not necessarily equal to dist of w, but it is eventually we would like to make dist of w equal to 0. So this is just notation that I'm introducing. So any questions on this? And now the algorithm I mentioned last time was the following. You want to maintain this array list of W, you initialize it using breadth first search. So this you will find some paths to every vertex that's reachable from W, and you will have a candidate shortest path length. And then we said you try to do these correction steps, okay, which is for each edge I, you check if, sorry, for each edge ij, so you check if there is some obvious improvement you can do, which is essentially you found some path from u to I of distance equal to this dist of I. Okay, that plus the length of edge. If it is, oh, I should, so yeah, so if the distance to I plus the length of the edge ij was less than the path you currently had from u to j, then you've got update. Okay, so then you were obviously suboptimal. So you just update dist of j to be equal to dist of I plus length of ij. Yeah.
So J would be W. J W is J in this case.
No, so W was an arbitrary vertex. J is the endpoint.
The same.
Sorry? No. V was always the same. Yeah, so in my problem statement, U was the source, V was the vertex we are interested in. All other letters, I will use them as temporary placement. So, yeah, so the point is that you define a dist value for every vertex. Even though you're only interested in the distance to V, you define this dist value for every vertex. Okay, so you maintain an array. So, yeah, that's probably. Alright, and what we are saying is if you have an obvious improvement, you can do it, and do this for every edge. Make this check for every edge, and you just keep repeating this process until the dist values stop changing. So at some point you will not notice any more improvements. At that point, they stop. Okay, so this is the whole algorithm. Okay, so any questions about the algorithm? Yeah.
So I'm trying to understand the diagram. So we have edge ij, which we have there, and the distance of j. That's the total distance to j from our starting point.
So remember, this j, the meaning of this j is just the current candidate we have. Okay, think of it as like the length of the path that you have found so far. It's the length of the shortest path that you have found so far. Okay. So that's dist of j. Okay. What we are saying is, if that quantity is strictly more than the length of the path we have found to I plus this length of ij, then update this. Then in some sense we have found a better path. So that's why we are updating this dist of j to this plus. Okay, to this. So yeah, so you can just think of this as you have some current paths in mind, and you're always trying to see if there are better paths. So that's that. Okay. So good. And a couple of things to observe is that at every point, this dist value is an upper bound on the true shortest path length. And this is obvious from what I have just said, because dist of W is the length of the shortest path we found so far. Right? So it can only be bigger than or equal to the length of the shortest path. So this is a clear thing. So it's because this W is this part is the function I. Another thing to note is that as you execute the algorithm, list of W only goes down. This is again obvious because you only improve. So, alright. And now we want to show that when the algorithm terminates, you actually have found the length of the shortest path. So we want to just show that the algorithm is correct. Right? And you want to show this for every task. Right? So how do we prove this step? So I guess I should not have had this, but usually, I mean, as we've been seeing, you want to prove something by induction. Right? So we want to say, so the question we ask ourselves is, can you say something nice about what the algorithm is doing after it executed for k steps or k iterations of this step? Right? So you have remember you have a loop here. Right? So you are doing this, then you are going back to this step. As long as you see some change. Right? So the question is, if you do k of these steps, which is for every I you update these this values, can you say something nice? Is the question clear? Okay, so we have, so this is the algorithm, right? So this is the main loop and you are running this loop multiple times. And the question is, if you ran this loop for k times, what would happen?
We know the shortest path for all nodes up to depth k.
Okay, so what he's saying is, this is a good guess, right? So you look at the original graph and you've got a bunch of vertices at every depth. And what he's saying is, if you ran this for k iterations, which is this edge update steps for every iteration, for k iterations, then for all vertices up to a depth of k, you will have the right distance line. Okay. So let's take a simple example of just k equals 1. Okay. So now just running this loop once. So it's like saying you've got these BFS values and you have 1, let's say 4, 5. And if you run it once, maybe some of the edges will get updated. But the point is, suppose there was a path which looked like this, okay, where you came to this vertex, which are marked as x, marked across. So you came to this vertex, and the shortest path length to that is 3, right, because the path around. Now, if you had just done one round of this kind of an update, you would still not have found it, right? Because with just one round, you would have found that there is a short path to this vertex. You would not have realized that there is a better path to this guy. Okay, not necessarily. Okay, so how do you? Yeah, but you're roughly on the right track, right? So in some sense, for nearby vertices, something nice is going on. So what would be a clean inductive statement that you can write down?
Every round is better than.
So this is certainly true, right? So this follows from what I've said before, because distance of W is monotone. So every round is certainly better than the previous round. Question is, why would it converge to optimum? like assuming the process stops, why is everything the optimal?
You can guarantee this W and the short is the one for all the paths length less than
Right, so that's roughly what he was saying, right? So he was saying that if you had a vertex at depth k, you're saying that after k iterations you found the right thing. And here we saw a counterexample, but that is not necessarily true.
the path length is the less than k.
Okay, so
all the paths will become found in the structure.
alright, so what he's I think trying to say, which is the right statement, is that let's consider all w's, all vertices w, for which the shortest path to w, from u to w, has length less than or equal to k. Okay. So what he's claiming is that for all such vertices, you have found the right value. You found the right values of this. So the claim is for all such vertices, as such is defined by this. You would have found the true shortest path. Okay. And so this is a slight modification of what he said, but this is the slight trick to this proof. Okay, so you say that I will order vertices by the length of the shortest paths from you to that vertex, and if the shortest path had length k, so you might say, okay, there might be vertices for which there are two shortest paths. Just consider the min of two. So that's what we're saying. So all right, and this is now a clean statement that we can prove by nothing. Right, so we want to say that after k iterations of this algorithm, you would have found the shortest distance to all vertices which the shortest path and length is. So how would you prove this time? We can start with what would be a reasonable base case?
For those that have depth 2, depth 1, with 2 iterations we will have found the
No, not necessarily. Because, right, so think of extending this example where you just have u here, and you go through a whole lot of one length edges, maybe like 10 of them, to get to some vertex w, but there was also one path here which was of length 100. Let's say, now this w is a depth 1 vertex, but its shortest path has length which is maybe 10. So if it had 10 such things, then it had a very large short. But the point that he mentioned is that this length is what matters. Okay, so the length of the shortest path to that vertex is what matters.
Can you look at the different examples of the one replaced by 3, and we run the algorithm only a couple of times, so 2 times?
Yeah, then it will work.
Would it work to take 1, 1, we still haven't found the shortest path, but the actual shortest path is 3 of depth 1?
No, No. So what do you mean by the shortest path of third step?
Also consider an example like the one we had where there's a chain of 10 ones.
Okay.
Making it there's also a single edge of weight 9, so that's obviously the shortest path.
Okay.
If we run the algorithm 4 times,
Yeah.
then we have to find the shortest path, even though it's a depth 1.
No, in this case, you coincidentally found the shortest path, right? Because the candidate path you have had for this vertex would have been 9, right? Because remember you are exploring every vertex. So you would have initialized the disk value of W to be equal to 9. Okay. It just so happens that it will never get updated to something better. So in your example. Yeah, so it's good that you are giving examples because the easiest way to understand these things is by playing with examples. So that's good. Right, but yeah, so the claim we want to show is this. Okay? If the shortest path has a certain length, then take that many iterations to find. Yeah.
So base case can say that k is 0.
Yeah, so you always want to choose your base case to be when the proof is very easy, right? So k equals 0 is a perfectly good base case. Because you have not done any step of the algorithm, and therefore, there is nothing to show. So, and there is only one vertex that has a 0 length path, that is U itself, right? So there is nothing to show. So suppose it holds for a certain k. Now consider k plus 1. Okay, so what happens now? How will you? Yeah. So what do we need to prove now?
Would it be that for the nodes of distance k, we have the shortest length of shortest distance k nodes away? Does that make sense?
I mean, yeah. Can you restate it trying to be more formal? I guess you have the right
So
idea.
you know that if we go through k iterations, we're always going to have the shortest path from U to W k distance away.
Okay, so I guess what he's trying to say is, we know by the inductive assumption that if you did k steps, okay, then for all vertices whose shortest path from U had length at most k, okay, or shortest path had at most k steps, that's what I should say. Shortest path has, I should probably not use the word length here, as number of hops. Because, I'm using length in 2 different ways, so I don't want to do that. Okay, so, so I want to consider all W for which the shortest path from V to W has number of hops less than equal to k. And for those vertices, this is our inductive assumption, right? That you have the right shortest path. Okay, so we know that for all vertices W such that number of hops in shortest path. This is the inductive assumption. We found it. And now you want to say something about. Now you want to consider a vertex that has whose shortest path has k plus 1. Okay. So yeah, so now let's consider any W prime such that shortest path from U has k plus 1 hops. I want to say that doing one extra step, one extra iteration in this algorithm, which is for every edge ij find this, will end up finding the shortest path to this W prime. So why is that?
I think we can separate it to two cases. If the new hop is a visit node and we have a new shortest path, then it will get updated.
If we have a new
And it has a new shortest path, then it will get being updated. If it haven't been visited before, then the path will automatically be being the shortest path.
what do you mean automatically?
Because if the hops, the new node haven't been visited before, then it only have one path to that node, and that path will be the shortest path.
Okay, so and if it has been visited before, what is your argument?
And we will check the new path with the old path, and if the new path is smaller, then we will update the path.
Yeah, so turns out you don't really need to make two cases because we initialized with breadth first search, so you would have visited every vertex that was reachable. So yeah, but what is our argument is that you look at the shortest path from U to W. So U to W prime. So it goes to something, and it goes to some last vertex, and then it's W prime here. Yeah, this has length k plus 1. Sorry? K plus 1 Yeah, sorry. Yeah, it has k plus 1. Right, so there's k plus 1. Okay, that's a good point. Yeah. So now, what he's saying is, inductively, I know that I have found the right distance for this vertex. Yeah.
Can I make clear something? Can you jump back to the slide of the means the distance is one more. Okay. Yes. Okay. So the distance j greater than distance I dot length ij. So that means the distance I here is the distance I of the last means the last loop or the distance I of the current loop.
Oh, I see. So, yeah, so you have to be careful about it in principle.
Yeah,
so his
maybe
question
have
is,
the order,
should we actually just consider of the previous loop, or I mean, do you update all these distances in one shot, or do you update them as you go along, and can you run into bad issues because of this? Okay, it turns out it doesn't matter. Okay, but if you want it to be clean, think of it as from the last loop.
From the last, yeah. Okay. If it's the current loop, maybe the order that we update the
Yes.
maybe it's a matter
Right.
of the order.
But the fact that these things are just monotone, turns out it doesn't matter. Because you would only use the better distance value, so the algorithm will still be chaos. Yeah, so, but that's a very good question. So what is the question here? Yeah, so you were just asking, I mean, if you do this, I mean, you may be, in one iteration, you may be updating multiple distance values in the same iteration, right? And and you are doing this weird comparisons, do you take the new value or do you take the value from the previous loop? Okay, so it turns out it doesn't matter, but if you don't want these kind of concurrency type problems, just think of just using stuff from the previous loop. So both of them turn out as fine. Okay, so alright, so this is great. Okay, so now we are considering some W prime for which the shortest path from U to W prime has k plus 1 hops. And now we are looking at this vertex, the vertex right before W prime on this path. And let's call it W W prime. So remember, we don't know this path. But yeah, so this is just for the purposes of analysis that I do this. So I want to claim that we would have had, at the beginning of this iteration, we would have had the right value for distance of W double prime. I want to say that why is this true? Well, actually, is it true? For distance of W double.
By the inductive process.
Sorry?
By the inductive assumption.
Yeah, so by the inductive assumption, you would think that this should immediately follow, right? I mean, it's almost true, except that you have to argue that the shortest path from U to W double prime has at most k hops. Okay? And I mean, this turns out to be clear because shortest paths have this nice property that if the shortest path from U to W prime goes through W double prime, then the path you have is also the shortest path from U to W double prime. Because if there was a shorter one, you could have taken that instead. Okay? So the shortest paths have what is called this optimum substructure type property. Okay, so let me just, this is just a technicality, but this is something unique. Okay, so all I'm saying is that optimum path from U double prime has number of hops less than 2 to 3. And the reason is this property that is called the optimal substructure property. Shortest paths. And this basically says that if you take the optimal, if you take the shortest path from U to W prime and you have a W double prime along the way, then this path is also the shortest path from U to W. So it's a very simple property. It's intuitively obvious, but you just have to state it, because otherwise it's not a priori clear that you would have found the correct value. So this shows that you would have had the correct value for distance double prime by the inductive assumption. Now suppose you had it, why would you, after you do one iteration, why would you have the right value for distance of W prime? remember you're doing one iteration, right? So what is the check that you do for W prime? I mean, suppose you looked at this edge, W double prime to W prime. What is the check that you do? This is something that you mentioned.
We need to check if the node is visited yet.
I mean, remember I told you, right? So visited us is not a problem anymore because you initialize with PL. Okay, so yeah, so if you are able to visit it, you would have visited.
So you look for other ways to get to W prime.
Right, but all I'm asking is when I'm doing the check, so each iteration involves doing this check and updating step for each edge, right? And all I'm asking is now, suppose you are at this edge, W prime, W double prime, W prime. So you will consider this when you are doing this iteration. Now the check you will do is essentially if the distance value for W prime was, which is essentially the candidate path you had from U to W prime so far, if that had a distance that is less than the candidate path to W prime plus this, plus the weight, plus the length of this, and you know that you had the optimal path from U to W double. So at the end of this iteration, you can be certain that you will have that this is a path that you at least considered. And maybe you update it, in which case you are not optimal. Or you had something better to start with, in which case it's fine. You are always doing as well as the short. I mean, you could have had a different path whose length is, whose total length is also the same cost. In which case you would not do that. So this is the reason the inductive step works, and you have this claim that for any vertex where the shortest path has k hops, you would have found the shortest path distance to those vertices after k. Alright, so now can you use this observation to bound the running time of the sample? So how many iterations can there be? Sorry? What did you say? Number of edge is one answer, depth of tree is another answer, but what is the tree here?
BFS tree. The BFS graph.
Why does the BFS graph count to
We checking each node for the previous node.
See, we are not doing updates on the BFS graph. Right? We are doing updates on the whole graph. But yeah, so can the number of iterations ever be more than n? And the answer is no, because I mean if we just argued that if you do k iterations, you would have found the shortest path to all nodes whose shortest path had at most k hops. You know that for every vertex, the length of the shortest path has at most n minus 1 hops, right? Because if it's the shortest path, you will never repeat a vertex. So you can't have more than n hops in a shortest path. And this shows that so for this reason, after n hops, you actually make no more update. So previous claim implies that after n iterations, we have found to all and this is it, right? So therefore, number of iterations less than or equal to n. And what is the time for each iteration? So each iteration is just this, right? So this thing. What is the time you take for each iteration? Sorry? Yeah, so each iteration, as I said, you check for every edge and you do a comparison. This is just constant time, and you do this for every edge ij. So time for each iteration is O. So overall, the running time is equals O. Yeah.
The number of iterations n, is that going to be the number of vertices that were discovered in the BFS rather than the...
Oh, I see. Yes. Yeah, so if you don't reach everyone in the graph, then yeah, you can reduce the number of vertices. Yeah, I'm just upper bounding that by n. So he's saying that if not all vertices are reachable from group, then you don't. So you just have the size of the connected component. You don't have the size of the whole graph. Okay. So yeah. So this is yeah, that's correct. So yeah.
This is same as in EV, right? Now the big stop
Yeah. I mean, m for me is the number of vectors, and n is the number of vertices. Yeah, so maybe this is, maybe I needed to remind you guys, but m is often a standard notation for the number of vectors, and n is a standard notation for number of vectors. Alright, so the one thing I would like to say about this algorithm is, I say a couple of things. Firstly, it's called Schimbel's algorithm, and it's also more commonly called Bellman-Ford algorithm. Okay. Sometimes it's stated slightly differently, but they are the same. Yeah. Right, that was the next thing that I was going to say. Okay, so the other point about this algorithm, which is kind of nice, is that it also works when you have negative, when some edge weights are negative. Okay. But of course, you should not have negative weight cycles, or else the number of times this distance vector gets updated could be unbound. So the only thing, so it turns out that our claim that we had, right, which is after k iterations, I mean, for all the vertices that had shortest path using k hops, you would have found the shortest path. That is true no matter what. Okay, so even if you had some negative weight. Okay, so this is something you can easily check. And in fact, this statement is true even if you had negative weight cycles. Okay, but it's just that if you have negative weight cycles, then you know, for those vertices, the k is infinite, right? So the shortest path is infinitely hop. Okay, so in that sense, it doesn't make sense. But even if you had, yeah, but let's consider a case where there are no cycles. So then this claim would still be true. and you would still have the property that after n iterations we have found the shortest paths to all vertices. Because all this relies on is that the shortest path to any vertex uses at most n hops. And this is true even now, because clearly it is a simple path, right? So it cannot use a vertex twice, because that would mean there was a cycle and you could have removed that cycle. So for this reason, even if you had negative weights, it turns out that the whole analysis works. So that's the other nice thing about this algorithm. So this works even. Now the question is, can you do better than this m times n bar? And of course, it takes only m plus n time to write down the graph. Right? You just have to specify the edges and the number and the vertices. Right? But this is using significantly more than that. So we can ask, okay, can you do better than m times n? And the other thing is, maybe we are doing too much, because we are handling even the case of more general graphs where you have some negative weights and so on. Okay? So suppose I told you all the weights were actually positive. Can you come up with an algorithm that's even faster? So this is what we're going to see, and this is the popular Dijkstra's algorithm. So this is, as I was mentioning last time, is one of the first algorithms. So this came out in 1958. This apparently it was also in some unpublished works a couple of years before that also. Okay. So the notes I have in the beginning, it has some plain historical note of this also. So the algorithm was around for a couple of years before this, but this was first published by Dijkstra in 1950. Alright, and the goal of Dijkstra's algorithm is to do something in some sense better than m times n. Although historically that algorithm came first. Okay. So I didn't mean to have all this stuff on this slide, but I have it. So, right. So, okay. So what is the main idea behind Dijkstra's algorithm? The main idea is you start off by thinking, by recalling the problem we had with breadth first search. Right. So remember, if you had a weighted graph, we said that breadth first search doesn't work because the shortest path is not the one that uses the least number of hops. Okay, breadth first search always goes and explores vertices. Like if this is U, and these were the vertices. Okay. So breadth first search would first find the ones that were directly connected to U. Then it would find these guys. So you always find vertices in order of least number of hops. And we just saw that the number of hops is not exactly, it doesn't exactly determine the shortest path. Like in this example, you could have had 1, 1, 1, and this is an edge 5. So from U to V, the shortest path is actually this 1, 1, 1. Okay, not the 5. And so the main idea behind Dijkstra's algorithm is to see if you can fix this. Like, how can you, like suppose I still told you to, in some sense, do some kind of a search out of U, but always find vertices that are at a certain distance from this vertex. Okay, where distance is now measured according to this weighted distance. So sometimes this is called ball bearing, right? So it's geometrically, if you think of the graph as some kind of geometric object, then in some sense you're starting around U and you're trying to determine which vertices are at a distance. Distance is now measured according to the edge lengths, okay? Which is at a certain radius r. Okay, and you're slowly expanding out. And breadth first search exactly does this, but in breadth first search things were easy. All the edge weights were 1, so you could just grow one by one. Right? So now we can't afford to do that because you have weights. The question is, how do you not do this? Right? So there's a motivation for this, is a setup for the algorithm. Yeah, and this is one of the key differences now between weighted graphs and unweighted graphs. Is if you have an unweighted graph, if you want a vertex at distance 2, it's a neighbor of a vertex at distance 1. Right? In theory. But in unweighted, but if you've got vertex, if you've got edge weights, then you could just have had a 2-length edge out of this vertex. So it's so there's many ways of getting a shortest path length of 2. Yeah.
So I don't know if this is also different, but if we have all of the edges, like the maximum weight over here is 5, then could we explore like a depth of 5 on all of the associated edges, or rather until all the edges add up to that same amount, and then do like a breadth search idea?
What do you mean?
So let's look, if we step down the middle one, we step down once, that's a value of 1. If we step down twice, we've done 2. We could keep stepping until we have a sum of edge weights of 5.
Okay.
But then continue like a breadth search type of idea. So we go to the next edge and step all the way to 5.
Okay. Yeah, so that turns out to be, roughly speaking, the idea behind Dijkstra's algorithm. Okay, so what he said exactly is that, so what he's saying is, if you had a picture like this, right, and maybe this was 1, this was 2, and so on, then what you would like to do is first you will find vertices that are at the smallest distance in some sense from this view, which are a circle with other, which are this vertex and this vertex. Okay, these guys are at distance 1. Now I want distance 2 from this view, right? So I can't take this edge because that would be a distance 3 from you. So I'm going to take only this guy. Okay, let's give weights for the other edges just to be clear. This is 2, this is 3. So the only vertex I will find is now, let me use a different color for step 3. These are at the red ones are now at distance 2, right? And there's only one such vertex. And yeah, so that's at a distance 2. At a distance 3, I could now take the edge out of this red vertex. Okay, so let's call it purple, and I could either take this vertex, or I could also take the 2 edge out of this one. Okay. So this is, roughly speaking, how you're going to build this this new breadth first search tree. So this is the idea behind Dijkstra's algorithm. Okay, so at each step, and the idea is to do it systematically by, instead of just looking at all these things, just add one vertex at a time. Okay? So that's the idea behind it. In some sense, it's extending real fast. And the main intuitive ideas are throw a ball of a certain radius around you. Okay, and do this a bit systematically. Add one vertex after another. Add one vertex. And now you can try to think of how you would implement this. Right? Suppose I have this picture. You would say my first vertex obviously is just you because this is at a distance 0 from you. Now I want to add one vertex of distance 1. And sometimes there may be no vertices of distance 1, right? But in which case I'll just look at the shortest distance I have so far, and I will add this guy. So in this case it's 1, so I've added the orange vertex. Now I realize that there is another vertex that had distance 1 from me. I'll add that guy. Doesn't matter the order which we have. Yeah.
Sorry, what would be the radius of the ball in this case?
Which one? So at the orange level, that would be the radius would be 1. Okay, and when I am at this, sorry, I don't know, there's 2 oranges there. There's light orange, there would be 1. This is supposed to be red. On the screen, it's showing up as orange also. Okay, so there the radius is 2. Okay, that's all. Yeah, so this is the idea behind right. So let me now write down the algorithm. Okay. So the formula is start with vertex here. And add. So you should think of what the exercise is doing as some kind of building a tree. So let me come to that in a minute. But you can either think of it as building a tree or growing some kind of a region. So we start with here. Add vertex V, W that has min distance to V. So that's this W. The reason I'm not doing the ball in integer intervals is because my weights need not be integers. Okay, so maybe I have some edge weight of 0.5, in which case I want to do the 0.5 first. So this is the reason you add the shortest. That has a min distance to you. And this is now what we have. And now you look for everyone. Now add vertex W prime that has the min distance to you, either directly connected to you or using the path that you've built to one of these things so far. Okay. Like you already established that distance from u to w is 0.5. So you use a direct edge from this to. You look at all the vertices that are connected to w. And maybe there was a 0.5 here and there was all the edges here that we had to. So in which case you want to add this vertex W. So, right, so W was a distance 0.5. You now look, so think of like drawing this ball just by adding the closest vertex that you have in all the vertices to your set. And your new set now becomes U, W, W prime. And keep doing this. So next you add something like that, where now you look for neighbors of this also. And for those guys, the distance would be 1 plus something. And that's how you grow this. Okay. So formally I have to specify how you do this kind of an operation. But intuitively is this operation here. That you try to grow this ball around U of different radii by adding vertices one after the other. So I'll pause here for a minute, so just in case you guys want some more explanation with more examples.
that second sets add vertex W prime that has
Oh, the same thing. Yeah. So remaining distance to the set UW, and distance to U is I just count it as the edge that I have to U. And distance to W would be like if you had an edge to W, then I would add the weight of length of that edge plus 0.5. That's what I mean by the closure.
I will be sure initially how to choose the radius from the view.
Right, so this is by the way I have defined it, you don't have to choose the radius at all, right? Because you're always adding the vertex that is at the minimum distance to you. So that becomes the radius.
It's kind of like a gradient algorithm.
Yeah. So in fact, I will say in a little bit that I mean this is supposed to remind you of the spanning tree algorithm that we saw a few lectures ago. This is actually almost exactly the same thing with a mild twist. Okay, so there also we essentially added a vertex of the least edge weight out of the set you've had so far. But instead now we don't look at the edge weights, we look at the distance that you get, and you add the vertex that has the least distance to the source. Okay. So yeah, that's a very good point. This is really similar to the spanning tree algorithm. Yeah, in fact, that's the reason both of them have identical running times. Yeah, that was the question. Yeah.
The W prime.
Wait, say that again. Sorry, I missed your.
For the second iteration, we had a with W prime that has member distance to U and then time.
Yeah, to the set U, comma W. So you look at so W prime could have had an edge to U directly, which will give you some length, and it could have an edge to W prime, sorry, to the W, which would have had, which in this case has a length of 0.5. All I'm saying is.
We have 100 1.5. We will never consider the two with N.
If you have one, sorry.
We have a bunch of
Yeah, I see. Are you saying if you had 0.5s like this, maybe 5 of them is enough, and you've got a two-way edge to this guy. So yeah, so in this case, what would happen? So this is a good example to test your understanding of the cell. Right? So this is U. So first you would find that this needs to be your W that you run first. And then you realize that these vertices are not even in consideration. They have no paths from the set U, comma W. So they don't have an edge to U, they don't have an edge to W. So all of these vertices are not even in consideration at this point. So the candidate W primes are this guy and this guy, because they are the ones that have an edge to either U or W. Okay, and for this guy the cost of connecting would be 2. For this guy the cost of connecting would be 1. So you will add this one. Okay, so this would be your W. Now you look at the minimum distance to the set of vertices U, W, W prime. Okay, the next step, it would be the same thing, add W, W prime that has minimum distance to the set U, W, W prime. Okay, so now your candidates are this vertex and again this vertex. Still this vertex is better. Okay, so you'll end up doing a W prime out here. In the next step, both are equally good. So maybe you did this again. But in the step after that, this one is certainly better. Okay, because this one would have 2.5. Because that's what you're saying, right? If you had like 100 things. So the next step, the fourth step would be this guy.
How do you consider the ratio of distances to the previous set that we found so far? So that was going to be also 0.5, not 2 point.
Oh, I see. Okay, so alright, I should probably define this. Okay, so minimum distance to you via this set. Okay, so this is what I meant. Okay, yeah, that's a good point. So all he's asking is, so if I did wrote this would be the spanning tree algorithm, but yeah, so I'm always counting the distance to you. Okay, so that was implicit in my writing. Okay, so we care about distance to you, right? So yeah. Right. So the same thing here. Okay, so it's minimum distance to you via this. Okay. So, and in fact, you've just pointed out the difference between this algorithm and the spanning tree algorithm. In the spanning tree algorithm, you don't care about reaching you; you just care about reaching the set that you've built so far. So, okay, so this is and this is the Dijkstra's algorithm. And you've got to ask yourself, how are we going to implement this? Right? So you, at every step, you've got to do these operations of finding the vertex to add, so that its distance to you via these set of vertices is as small as possible. And what is this? I mean, so if you want a data structure that somehow lets you find the minimum element you have pretty quickly and do updates pretty quickly, turns out that the priority queue is what you should be thinking of. Okay, so we want a data structure that maintains U and this, I will call this candidate distances again disk of U. Sorry, W comma candidate W there. And we want to quickly obtain the W that has the minimum disk value. And it turns out the other thing we would like to do is quickly update the disk value. Yeah.
This right now means it's referring to the new algorithm, extra.
Yeah. So that's what I was. But disk of W is now redefined. So disk of W is redefined to be the minimum distance to via the set. So we are growing a set one element after another, and I said in the first iteration I find the W prime, or rather in the first iteration I find the W that has the minimum distance to U. Second iteration I find W prime that has minimum distance to U via W and the U itself. The next step you have this U, W prime. And you keep doing it, right? So at each step you have a set so far, and distance W is now defined to be the minimum distance to this the other set. So in each step you want to find the vertex W that has the minimum value for this notion of distance. And now these distances get updated because when you add a new vertex, so you have this set that you are building. When you add a new vertex, let's call it, instead of having W superscript with many dashes, let's be a bit more common and write them as W1, W2, and so on. So after some number of iterations, you added W2. And in the next step, let's say you added W of k plus 1. And now your set grows to include this k plus 1. And now for every vertex, you've got to now consider the distance, not just using these guys, but also potentially using wk. So that's now the disk value. So you've got to update these disk values. This is the reason we want to update the disk values. And we want a data structure that can do both of these very quickly. So it turns out that the priority queue, if you implement it natively, it does both of these things in time overflow. Okay, so if you do it a little bit smarter, you can do things. You can do some of these operations. Alright, but this is the algorithm. Okay, so you have this new value for distance, and this is like again a candidate distance like we had last time. And this is how you update. Okay, so let's not go too much into how you maintain this and how you change this. Okay, so this is this is actually you should read because it's not particularly interesting. I mean, it turns out that you have to do the natural thing, which is when you are adding this. When you added a wk plus 1, you don't update the disk values of all the vertices. Just update the values of vertices that are reachable, that have an edge out of wk plus 1. Okay? Because those are the only values that could potentially get updated. Right? Because your new disk value for some vertex which is not in the set so far is the best disk value to do using the vertices u w1 through wk plus 1. There is no edge to wk plus 1, then it would just be the previous value, right? So you don't have to update. Okay? So this is the reason each addition, you can say that it takes time that is proportional to the number of edges of the vertex you're adding, out of the vertex you're adding. Okay? And so this is again a standard thing. So I want to do this. Okay, so it turns out that if you implement it like this, this only takes time for m plus n times 1. And the other thing which I should mention is that people have improved this to m plus n log n. But I don't think we know how to do just m plus n. Okay, so this is one of the problems. Okay, alright. So this is the algorithm. Okay, so I still haven't shown the correctness of the algorithm. Right? So and it turns out that correctness is actually kind of nice. Okay, so and this is now using a much. The claim here is even simpler than the claim earlier. So the correctness claim is whenever we add a vertex W to the set we are maintaining. Think of it as the ball we are with. The disk this is the key claim. Okay, so you are in some sense growing this ball. We are saying that when we add a vertex W to your set, at the time you're adding, you would have already found the shortest distance from U to that. Okay? And intuitively, if you think about it, this is somewhat, in a sense, it's very easy to see, right? So let's take vertex U, and let's say we are arguing about the moment you are adding the vertex W. Okay. So I have already said that you have drawn a ball, and you have all these vertices. And moment you're adding this was the vertex that had the shortest distance to the stuff you added so far. Okay. Now, what would the shortest path from U to W look like? It would take some path, and it could have gone like this. But my claim is that it could not have been like this, because then the distance from this guy to U would have been shorter than your candidate that you're finding from W to U. Okay, and that's the reason you must have had a direct edge that went from here to this stuff. Okay, and now you know that by the inductive hypothesis, for all the vertices that have been added so far, you have indeed found the shortest path. Okay, and therefore you have found the right distance value for this. And therefore, when you are adding it, you also found the right distance value for that. So as we are out of time, I leave. So this is just a overview of the proof, and yeah, but this is the main end. So it's very simple.